The color of soap bubbles is a good example of thin film interference. This is a phenomena of wave optics which occurs at a very small scale. A thin film is simply a thin layer of transparent material sandwiched between two other materials. For example, a thin layer of soap between two volumes of air. Imagine three different media represented here as hollow rectangular frames laying horizontally. The middle medium represents the magnified view of a thin film between two other media. The relative indices of refraction for each medium are represented by the depth of each rectangular block as a visual reference to the relative values. Incident light will move in from the left and proceed through the arrangement for the demonstration. The width of the middle block is proportionate to the thickness of the thin film as measured in multiples of refracted wavelengths. Note that if the index changes, the refracted wavelength also changes. The thickness of the middle thin film medium doesn't change, but does represent a different multiple of refracted wavelengths depending on the amount of refraction. The distance traveled by the beam within the thin film medium is equal to approximately twice the thickness of the medium. When there are two emerging outbound beams of light, the resulting interference pattern will be shown on the left. First, we begin with a series of media with increasing refractive indices. As the incident beam enters from the outside medium, it encounters the boundary between the outside medium and the thin film. At the boundary, part of the beam is reflected and part is transmitted. The reflected wave is emitted inverted or upside down since the reflecting thin film has a higher index. If the reflected index had been lower, the reflected wave would have come away right side up. As the beam progresses through the thin film of the center medium, notice how the refracted wavelength of the transmitted wave within the medium is compressed, since the larger index causes the average velocity of the wave to become slower. At the second boundary, once again, part of the beam is reflected and part is transmitted. The reflected wave is again emitted upside down since the reflected inside medium has a higher index. As the second reflection emerges and interferes with the first reflection, the combination shown at the left represents what is seen. Changing the relative index of the thin film medium will change the number of wavelengths traveled within the medium and therefore the resulting phase of the second reflected beam. This changes the resulting superimposed waveform. Changing the actual thickness of the thin film's second medium actually accomplishes the same thing. Additionally, lowering the index of the third medium will cause the second reflection to be emitted right side up and effectively shifted in phase by 180 degrees. Different colors of light have distinct wavelengths that will be affected differently by the same thin film. This will result in some colors being suppressed by destructive interference, while other colors will be enhanced by the process. The final product is a surface which shimmers with a variety of colors, even though the thin film itself may contain no pigment. In industry, thin films can be specifically designed to enhance or remove target regions of the electromagnetic spectrum. In nature, thin films produce striking arrays of unexpected color, adding to our appreciation of the world around us.